All righty, what we're gonna, oh shoot, sorry, I've already screwed up. All right, what we're gonna get into now is solution stoichiometry. This works exactly the same as everything else we've already done. We're just kind of putting a new flavor on it because we're in solution, okay? And we're gonna come at this from two main directions. But one thing I want us to get into first is to say that now that we know about electrolytes, we said strong electrolytes dissociate completely into ions in solutions. So what this means is if you have a strong electrolyte in solution, all of the ions are related by moles to the original formula. So for example, if we had, why, what the, uh, okay, if we have potassium sulfate, right, there's two potassium, so that means we have two potassium. And there's one sulfate, so we have one sulfate. And so then we get potassium sulfate that looks like this, okay? What this also means is everything is related directly by moles. So if we had 0.35 molar K2SO4, okay, then that means that we have 0.35 molar sulfate and we have 0.70 molar potassium, right? Because there's two potassiums in there. So we could say 0.35 moles per liter of K2SO4. And we know that 1 mole of K2SO4 is 2 moles of K plus. And yeah, then that's it. That's all we have to do. Then this is 0.70 molar K plus. That's where that comes from. Okay. We can get the conversion factors out of the formula, right? And we also said before, if we wanted to talk about oxygen atoms, we could say there's 4 oxygen atoms. We're going to focus on ions in solution because we're not going to have loose oxygen atoms. All right. Let's take a look at this. Stop being dumb, PowerPoint. Good Lord. There we go. All right. So let's have aluminum chloride. Aluminum chloride is AlCl3, and we have a solution that is 1.03 molar aluminum chloride. Okay, we want to know what is the molar concentration of chloride ions in this solution. Oh, my notes say 1.02. So let's make this a 2 so I don't screw up stuff all over the place. Okay, 1.02 moles of aluminum chloride per liter. We know aluminum chloride has 3 moles of chloride for 1 mole of aluminum chloride, right? Because there's a 3 in our subscript. So this is 3.06 moles of chloride per liter, which is 3.06 molar chloride. Okay, does that make sense? There's 3 in the formula, so there's 3 moles for every 1 mole. Okay, let's look at another one. All right, if we've got sodium carbonate now, what we know is that the solution has a concentration of sodium ions. So, right, so we could say this as the sodium ion concentration is 0.124 molar. We want to know what is the concentration of sodium carbonate. This is kind of the backwards of what we just did, okay? Because we can relate all of these coefficients and subscripts through the formula, okay? Start with what we know, 0.124 moles of sodium in 1 liter. We know there's 2 moles of sodium for 1 mole of sodium carbonate. And then that's it. We end up with 0.0620 molar sodium carbonate. Okay, not too terrible. At this point, I want to say that our secret word is Wolfgang. I wanted to have it earlier, but I guess I didn't. So there it is. Okay, secret word is Wolfgang. All right. Now, ions in solution work this way. So we can figure out how many numbers of ions and stuff are in solution. We can also do reaction stoichiometry in solution. Okay. So if we look at this example, what do you have? How many milliliters of, so here's our answer. It's going to be milliliters of HCl. 1.25 molar HCl are needed to react with 3.667 grams of zinc sulfide, giving us an equation. So we have grams of zinc sulfide, we have HCl, we have molar mass over here. This works exactly the same as doing it with grams and moles, except instead of using molar mass, we can use the concentration. Okay, let's see how this works. Start with the thing that has 1 unit, so that's our 3.667 grams of zinc sulfide. We're given the molar mass, so 1 mole of zinc sulfide is 97.48 grams of zinc sulfide. Ooh, excuse me. Now our equation tells us 1 mole of zinc sulfide needs 2 moles of HCl, right? That's our coefficient. So 1 mole of zinc sulfide for 2 moles of HCl. And we are told this HCl that we're using is 1.25 molar. So that's 1.25 moles of HCl for 1 liter. Okay. We're also told that we want milliliters of stuff. So let's do milliliters. 1 liter is 1,000 milliliters. Don't get it backwards. Okay. And we'll math it all out and we'll say this is 60.2 Schmidt 2073 milliliters of HCl. Okay. Oh, shit. We need to get sig figs. Our concentration has 3, so we'll round this to 3. This is 60.2 milliliters of HCl. Okay. All right, let's do one more and say, okay, what volume of 0.325 molar lithium phosphate is required to precipitate all of the iron from 175 milliliters of 0.156 molar iron nitrate? Okay, we're given the balanced chemical equation. Okay, we need lithium phosphate and iron nitrate. So what we're doing is we're saying, okay, we're going to add lithium phosphate to this 175 milliliters of this. So remember, we're looking for that word of again here. So this is going to tell us this is our start because we have a lot of stuff going on in here. Okay, so let's do that. 175 milliliters. This is iron 3 nitrate. Gotta get our milliliters to be liters, so that's 1,000 milliliters in a liter. Our concentration tells us that 1 liter of iron 3 nitrate is 0.156 moles of iron 3 nitrate. Okay. Our reaction tells us that 1 mole of iron 3 nitrate needs 1 mole of lithium phosphate. Okay. And then our givens tell us that we have 0.325 molar lithium phosphate, so that's 0.325 moles Li3PO4 for 1 liter of Li3PO4. I'm going to go ahead and do one more step to take this to milliliters because that's what I did for my notes. And we'll say 1 liter is 1,000 milliliters. All right. Now, if you're looking at this, there's a lot going on here. You don't have to put the thousands in your calculator. You're going to divide by 1,000 in the beginning and multiply by 1,000 at the end. That doesn't matter, right? They're going to cancel each other out. So you don't have to do it, but you have to show it, okay? Because molarity is in terms of liters. All right, math this out. We get 84.48 milliliters of lithium phosphate And we want 3 significant figures because all our data has 3. So this is 84.5 milliliters Li3PO4. Bam, bam. Okay. If this doesn't make sense or you need help with anything, let me know. Um, we'll get through this. You have plenty of practice stuff coming up. Let me know if you need anything. I'll be here.